Good evening to one and all. Today our chief guest Dr. Umesh P.K. Sir, BE M.Tech IIT Madras Ph.D. Professor Department of Civil Engineering, Vidyavardhaka College of Engineering, Mysuru. Introduction about Dr. Umesh P.K. Sir. Dr. Umesh P.K. Sir is currently working as a professor in the Department of Civil Engineering at Vidyavardhaka College of Engineering, Mysuru. Dr. Umesh Sir received his BE degree in Civil Engineering from Malnad College of Engineering, Hassan, University of Mysore in 1980, securing second rank. M.Tech degree in Structural Engineering from Indian Institute of Technology Madras IITM in 1982 and Ph.D. degree in 2002 from University of Mysore. Dr. Umesh Sir joined CSIR (Structural Engineering Research Centre), the Madras as scientist during 1984 in computer-aided analysis and design and computational mechanics. He served as a head of Tower Testing Research Station of CSIR SCRC, Chennai. He was actively involved in research and consultancy for more than 3 decades. He has handled more than 10 crore sponsored and consultancy projects for government and private companies, national and international. He is presently guiding 2 Ph.D. students. He has guided 30 M.Tech students in structural engineering for this dissertation work. He has published 37 technical papers in international and national journals and presented 71 technical papers in conference. He is editor for 2 books. He has filed 4 Indian patents. Area of research includes computation, structural mechanics, alternative construction, minerals and materials, the parallel computing techniques, metal structures, power transmission line towers, telecommunication towers and finite element analysis, corrosion and fire effective on metal structures. He is a German Academic Exchange Service (DAAD) Fellow at Ruhr University for 2 years 1990 to 92 to carry a research work on parallel computing techniques for structural design optimization of large structures. He visited the research center Aachen, Germany on technical assignments during 1997. Honors awards received: DAAD Fellowship Award for carrying out of advanced R&D in parallel computing techniques for the year of 1990 to 1992, DAAD West Germany. CSIR KFA Billrater Program for carrying out advanced R&D in parallel computing techniques, DFG June 1997 to August 1997. CSIR Technology Prize Certificate for Appreciation Scientific Contributions in the Development of Advanced Computation Methodologies, Modeling Techniques and Software Development, CSIR 1999. Award for Parallel Computing Techniques Excellence in High Performance Cluster Computing, 2004. The team of C to receive the Corrosion Awareness Award 2014 for Excellent Laboratory Award in recognition of meritation contribution to the field of corrosion science and technology by NACE International Gateway India section. He awarded Dr. J. Krishna Prize from Institution of Engineers India for the best paper in the journal Institution of Engineers series during 2016. The awarded Sri Arthur Cotton Memorial Prize from Institution of Engineers India for the best paper in the journal Institution of Engineers series during 2019. They awarded the best project of the year 2020 from Karnataka State Council for Scientific and Technology for my student project on experimental investigation of spherical shell roof using bamboo reinforcement 2020. Awarded the Best Project of the Year 2021 from VCE for my students' project on analytical study on feasibility of telecommunication tower using bamboo. The professional appreciations, the Fellow of Institution of Engineers, the Fellow of Indian Congress Institution, the Life Number Indian Association of Computation Mechanics, Life Number of Indian Geotechnical Society, Life Number of Indian Society of Technical Education, Life Number of Computer Society of India, Life Number of Advanced Computing Society, the member of Editors Board, Indian Journal of Environmental Engineering, Blue Eye Intelligence Engineering and Science publication. The reviewer of the following journals: the Journal of Institution of Engineers Series A, the Journal of Structural Engineering SCRC Chennai, the Journal of Computer Aided Civil and Infrastructure Engineering, the Intern Journal of Chemical Engineering and Material Science, then Journal of Civil Engineering and Construction Technology. Sir, thank you for this valuable time to for this section, sir. Thank you, sir. Yes, yes, sir.
So now we will start for our work. I will share my PPT.
Okay, sir.
So that whatever questions we have, we'll take up at the end. I will give around 45 minutes. I'll take up that presentation.
Okay, sir.
Then we will have a discussion around 10 to 15 minutes. Okay.
Yes, sir. Sure, sir.
So I will share my PPT now.
Yes.
Just mute my.
Yes, sir. Yes, sir. Now it's visible, sir.
Today I'm going to talk on design of communication towers. So, I worked in SCRC before joining as a professor professor of civil engineering at Vidyavardhaka College of Mysuru. Okay. As a chief scientist at the CSIR Research Center. Okay. Today I'll talk as for the design of communication tower. My overview of the talk will be, I'll make a slideshow. Okay, now it is visible, no? So if it is not visible, please tell me if it is. Okay. Hello. Hello.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yeah, if you're not able to hear me,
Yes, the voice is audible, sir.
Okay.
Okay, sure, sir. Sure, sir. Yes.
So my overview of my talk will be introduction, types of towers, design consideration parameters for the communication tower, what are the provisions of IS codes, how to calculate the loads, and what are the permissible stresses, structural analysis, and design of tower members. So there are so many towers you might have seen within the city and outside city. Like this, in rooftop towers, you might have seen so many rooftop towers within the city. So they will be having a lot of antenna on the tower, and you might have seen all the things. So how to design these towers? It's a question. It's all cantilever towers. So all the antenna will be hosted along the tower. It will be having maybe dish antenna. It's called dish antenna, or GSM antenna will be there, or different antenna, AG antenna, like different types of antenna will be there. All these are using for the communication of. You can see here. This is TV tower will be there. TV tower, steel TV tower will be there, or concrete TV tower will be there, and this is another type of microwave tower, and this is called pole type tower. It's having only pole. It will be having that one, and another one. You can see here number of antennas it will be posted at the top of the pole. And you can see for the police or telecommunication or communication between place to place, they'll be using the guide towers. So if you have a large area, they'll be having a guide towers like this. So usually it requires a large area for the tower. It will be one mast will be there at the center, and it will be tied with the guy ropes at different levels. So it will be like this, and it will be very economical, but it requires large area. That is our advantage here. So usually if you see this tower and tower-like structures are the two major infrastructures of transmission of electrical power or telecommunication and broadcasting. Okay, the towers are highly repetitive. You might have seen there are so many towers in everywhere. Either it may be electrical power or communication tower. It has to reach the from one place to another place. It will be having the same line of sight. So communication towers will be having the same communication line of sight. It will be repetitive, and hence we should have analysis and design should be highly competitive. So towards the commercial solutions. So what you want to do, you have to optimize the tower design so that the minimum weight will be there and optimum efficiency will be there. That you have to see. So these towers may be using for the different telecommunication. Today, I will talk only telecommunication broadcasting towers. Power electrical power transmission lines I will not take up today. Only telecommunication broadcasting towers. So mainly what are the telecommunication? Micro towers will be there, television towers will be there, radio transmission, receiving signals from the satellite. For that also they will use towers, and receiving signals from the air traffic control. These are the different, maybe some other different types that also will be there. So we'll see how we're going to design this type of towers. So what are the main parameters of these towers? So there are different types of towers. That is a tapping section. So monopoles I have shown, it will be having from top to bottom monopole. So it will be having a circular hollow section or square hollow section. That is the one thing, it will be only hollow section. Another one, it will be lattice structure. Lattice structure means it will be connected by different angle sections. Or it will be tubular connected. Guide towers you have seen, it will be guide tower on the mast, center mast will be there, and it will be connected by different guys. So for that one, it will be large areas required. And another one is a type. So these towers may be constructed in the plain area, hilly area, urban area, or offshore area. So these are the different terrains will be there. Then how it will be affecting these terrains also we'll see. And what are the loading condition? Loading condition may be wind load, cyclonic load will be there, and earthquake load. So different types load, how it will be affecting for this design of these towers. So here first you have seen the lattice tower or guide tower or monopole, and here a type of terrain type, and here the loading condition. So types of tower, self-supporting tower. That means whatever having directly on the ground, it's called self-supporting tower. And guide tower, as I told, it will be guide with the guys. Rooftop tower. In the city area, they want to use the rooftop tower on top of the existing building. So we have to take a lot of how to design a rooftop tower is very interesting, and they have to take the consideration of the building height and what's the condition, what the health, the monitoring of the building also have to see, and height of the tower. Its height also it depends. It may be 50-meter height or 20-meter height or 100-meter height or 150-meter height. So height also it matters because of the wind load. Wind load it varies from base to top actually. Because of that one, the height also is very important. And the cross section of the lattice tower, it may be square at the bottom, or rectangular, or triangular, or it may be hexagonal, or it may be in the circular portion also. The types of structural members, or what as you told earlier, maybe tubes or angles or hybrid. Hybrid means it will be tubes will be there and angles also will be there. There's a different types of that one. So once if you see that one, what is the condition? So different parameters. These are the parameters you have to consider for the design of towers, starting from the type of structure, terrain type, loading condition, type of tower, height also very important. Cross section. Cross section also is a square. It will be having a diagonal wind will be grounding actually. There also have to see rectangle, triangular. Of course, a rectangle is similar to square only. Triangular, it will be having a load acting on the normal surface and also from backside also to consider. And tubular sections is very economical, but it attracts very less wind load. That also very important. And this angle section, because of flat section, it will have more wind load. So if you see in the design parameter, the wind IS code also very important. What code you are going to consider for the design of this telecommunication towers, that also very important. Some usually previously used to have IS 802 as the code for the design of telecommunication towers also. But now they insist that you should go as per IS 800 2007 for the design of the telecommunication tower. If somebody wants to have IS 802, they should have the what is the load factor. It doesn't have any load factor. It's the code for the power transmission line towers. So mainly there is a lot of transmission towers will be there. They want to optimize the weight, and hence they doesn't have any load factor. So if you are going to consider for the telecommunication tower, you should use the load factor. And type of sections, it will be there in 808 or 1161 that you have to use for the type of sections. And another one, it will be material used for the tower members. The grade of steel gives in IS 2062. And the wind load, I think we might have seen the different IS 875 codes for part 1, part 2, part 3, part 4 like that. Part 1, part 2, of course, it will be dead load and live load. It's the IS 875 part 3. It has been revised in 2015. This is only for the wind load conditions for buildings and structures. They'll go in general. So for all the types of building and structures. And IS 1883 part 1 2016 is the criteria for quick resistance design of structures. So that also provisions for the buildings. And this another code, it is 1893 part 4. It gives criteria for the quick resistance design of structures for the industrial structures, including shaft-like structures. Here they includes the transmission tower and telecommunication tower. So if you are designing a telecommunication tower, you have to see into consideration 1893 part 4 also. So that is very important. So we'll see how these codes will be taken for the loading condition. So I'll talk about wind load and quick load. See now. So what's a component? First, let me see what is the component or what is the anatomy of a tower. So tower means it will be having the panel. What is a panel? I will explain that one. What's a leg member? Bracing or diagonal member, belt or horizontal member, redundant members, gusset plate, cover plate, lead, nut and bolts will be there. So generally, you might have seen the tower, it will be like this, full towers will be there. Okay. So one from here to here, that color differentiation you might have seen that one. This is called one panel. So there is one panel will be there, this panel. So tower, it will be having the main members 4 or 3 or 6, it will be there, projecting from the ground level to the top. That is called leg members. So leg members will be there. And see here, if we have the diagonal members, also called bracing members, main bracing members. So it will be there here, main bracing members. It may be K bracing or it may be X bracing like this. And in between, they will be having the secondary bracings. This secondary bracings, it will be used for the reduce the buckling factor. So if we have a tower leg member from here to here, if you want to reduce the buckling length, where that is very important for the compression design of members. So in that case, you can have the secondary members so that the buckling length will be reduced. So if we have divided to 4 means, so total length divided by 4, that is buckling length for the compression, it will be reduced to 1/4. So like that, different panels you can see here. This second members, it will be here, you might have seen here in the tower also. So here you can see what is gazette plate. Gazette plate, it will be connected from the like member, it will be there like to the facing member. They will connect with the nut and bolts. This is gazette plate. So here this cover plates. So you might have seen the one member to another member. They will be connecting cleat angles as well as this cover plate. Cover plate will be there outside, and cleat angle will be there inside of the this angle. This is a main leg member projecting from here to here. So they want to connect at this point or at the every 6 meter length. So that they will be providing outside, that is called cover plate. It's not fully connected. So here you can see all the bolts will be there, and inside also will be having a cleat angle. So you might have seen that single shear, double shear. So if you provide cover plate as well as the cleat angle, it will be double shear will be there. So this is the gazette plate you can see here also. Just they're trying to connect this one. And here you can see this is called cleat angle. It will be inside. So this angle member will be used for the tower. It is actually star angles. Star, you might have seen that two angles will be connected by like this. It will be there, and also they will be having the cleat angles here. So from here to here, connecting from one leg to another leg member, it will be connecting at this point. So you can see a number of ports, so many number of ports, and leg members, it will be very heavy. If you want heavy load, in that case, they will be using the star angles for the tall towers. For small towers, it will be only maybe 100 by 8 will be there, 110 or 130 will be there. For 150 meter height and all, if you see TV towers and all, they should use uh, star angles. Star angles means two angles will be connecting at the here. So here you can see here once again that cover plate as well as the plate angle will be there. So this is the tower. It will be having so many antennas will be there, and here the platforms will be there. So for the platforms, we provide 20-meter level to for the medians of these antennas, or if you want to paint or whatever it may be, they will be providing rest platforms as well as working platforms. They say. So both will be there in a tower. So design towers, design parameters, if we see top and bottom, it's also very important. How you are taking the top width, what is the requirement of top width? So if you want to provide the ladder inside, the top width is also very important. That is the minimum vertical curves, restricted area. So if you want to reduce the width, bottom, if you have a reduction, it will become very narrow, and the foundation forces will be more. And if you have a large area, you can increase the base width, foundation forces will reduce, and you have to optimize the weight as well as foundation forces. That is also very important. If you cannot have large base, if you large base width, the bracing members will become more. So it will increase the weight of the tower. So you have to optimize both on that one. And geographical location of the location for wind and earthquake loads. So you might have seen that IS 875 and 1893, it divides for our country into different zones. So you cannot use the same tower in all zones. So that is very important. So I will show you that on how it will be varying our India for wind as well as earthquake load. And this angle of twist and sway, that is also very important in the telecommunication tower. Why? Because the line of sight, whatever line of sight is there from tower to tower, if you have a cyclonic wind, you should not twist more. If you twist more, the line of sight or the signal which is lost. Sometimes you might have seen your mobile will not get that signal. So if you go some other direction, you will get it. So that also it will be possible. And type, number, and location of antenna. So these different types of antenna, whether antenna, GSM antenna, and dish antenna, different types of antenna will be there. They will be providing, you see that in the tower, they will be providing at a different level, and also that orientation, whether it's very orientation towards the wind or opposite to the wind. how to take the shielding effect, all the things very important. And I told you that load factor, if you are considering for the IS 802, you have to consider the load factor. Climbing facility and cable rack. So this climbing ladder is required. Either the ladder can be provided outside the tower or inside the tower. This will be required to climb for different levels. So if you provide outside, it's again a wind load. If you provide inside the tower, you can reduce the wind load on the climbing facility. This cable, you might have seen that one. So many towers will be cables will be running from top to bottom. So they will be providing the cable rack so that they will tie it in the cable rack so that it will come down in a line without any disturbance when wind is blowing. And also location of platforms that also attracts wind load. So that also very important towards the location of the wind platforms. So computation of loads, the thing on the tower it will be wind load on the tower members. You might have seen the tower members are very skeletal. It doesn't have any wind load and all. So it will be having more wind load than our other buildings also. So antenna, what are the types of antenna, ladder, platforms, members, all the things it will be attracted by for the wind load. And wind load of the tower members, antenna, ladder, platforms, and their mounts. That also have to consider. Live load on the antenna platforms and direct platforms, that also required. Seismic loads you have to consider. And similarly, miscellaneous loads like erection loads, temperature loads, ice loads in different area of country. You have to consider the ice load, either the ice load or temperature load. The erection load is required to erect the tower in different heights. So wind load, if you consider in the tower in our India, wind load is the most important of all. It often governs the design. Whatever it may be, the wind load it affects. So in India, I have seen a lot of towers we have designed. So far, we have designed towers governed by the wind. So dynamic effect due to wind. So another criteria is called. So if we have a natural frequency of the tower is less than 1 hertz, I think I mentioned here, less than 1 hertz, then it will become very dynamically sensitive. So IS code specifies either the natural frequency less than 1 hertz or will be height by P ratio greater than 5 hertz. Then dynamic effect has to be considered. In most of the cases, a tower up to 100 meter, dynamic effect will not control. Okay. Live load usually will be negligible. Why So live loads, when cyclone is there, nobody will climb the tower and do the work. So that's why live load will not be considered for the combination. Only dead load and wind load or earthquake load. You have to consider that way. Seismic load is considered some of the case. Mass, if we have a large mass at the top level of the structure, that is heavy mass, then seismic load will be governing. In the zone 5, usually in the northeast zone or in the Kashmir zone, it will be governing. Kashmir zone and northeast also, ice load also will be there. So for all this load condition, we have to follow IS 875 for the wind load, IS 1893 for the earthquake load. So if we see in IS 875, the design communication tower is primarily ground by the evaluation of wind loads and their responses. That wind velocity varies in a random manner, both in time and space. So IS 875 gives the basic wind speed. Basic wind speed is called the 3-second gust velocity at 10 meter height in category 2. I will tell what is category 2. In category 2, is defined as the basic wind speed. That is a 3-second gust velocity at 10 meter height. In category 2, it's called basic wind speed. So entire country divided into 6 regions. So it will be having the basic wind speed 33 meters per second, 39.5 750 and 55 meters per second. So 6 zones they are divided. So basic wind speed have been worked out for a written period. So for a written period of 50 years written period, the designer should select the basic wind speed depends upon the location of the tower. So where you are locating according to that one. So if you see here, this is the tower. So you can see the basic wind speed. So this coastal region you can see here, that is having 50 meter per second. That is 180 kilometer per hour. So you can see here in the northeast zone or in the Kashmir zone, that is a 55 meter per second. That is a 200 kilometer per hour. So if we have in the south, except in the coastal region, in the south in either Karnataka or Tamil Nadu, it will be having either 30, 39 or 30, 33 or something like that, less than only. The blue it will be 33, this will be 39, 40, 47 like that. So the difference is that, so whatever tower you have designed for the Tamil Nadu or Karnataka, it may not be applicable for the northeast zone. So because that is a different wind speed will be there. Wind speed is very, very important. Then basic wind speed. So basic and also height of the tower. I'll just show you that one. So if you see here, so wind will be blowing this one. As the wind blows, it will be zero at the ground level and it keep on increasing so the wind speed, it will be variation will be as the time and space, it will vary that one. So it will be having the across wind effect and also along wind effect and also it will be having torsional load effect. So all the three effects you should consider when designing the tower. So it will be, I told you, it will be random in time as well as per space, affected by height above the ground, terrain category, structure or gust size, averaging period. So all the things it will be varying that one. So the whatever basic wind speed, use only the basic wind speed for that region. So we need to calculate the design wind speed. That is called at a different height. So if you take 10 meter only, they're giving the basic wind speed. If you take 11 meter, it will be different wind speed. Again, at 20 meter, it will be different. How to calculate that one? So yes, 875 gives the formula, rational formula for the design wind speed. That is using the basic wind speed and K1, K2, K3, K4 factors. So it will be depends upon the K1 probability factor, terrain category height, and structure size and factor. And K3 is a topographic factor, and K4 importance factor for cyclonic region. So 1.3 for post-cyclone importance and 1.15 for industrial structures, it will be the K4. Recently in 2015, they introduced K4. Previously, they used to have only K1, K2, K3 only. And you can see here how you. So for example, the K1 factor, risk probability factor. The factor K1 is based on the statistical concept which take into account the degree of reliability required and mean probable design life of the structure in years. So if you see in the IITM table 1, it gives the K1 factor for different wind speed and different class of structures and the probable life of the structure in years. So if you are interested to design any structure for any general structure, building or structures, you will be considering only 50 years. So for all the wind speed, it will be one value. That's why it will be, you can see here 1111. So we are interested to have for communication tower and buildings. So we should consider the probable life of the structure will be 100 years. So you can see the values for K1 for different wind speeds. It will be varying from 1.05 to 1.08. So it will be very small variation, but it will be having 5% to 8% variation. So that is K1 factor. K2 factor, it depends upon the terrain category. What is terrain category? There are 4 terrain categories are there. First terrain category represents open sea or lake or unobstructed coastal area of land. So So if you see in the coastal area, if you take a coastal of Tamil Nadu, it will be having a no obstruction. So that will be considered as a terrain category 1. So if you come, terrain category 2 is defined as the with scattered obstructions representing rural area. So it will be having only scattered obstructions similar to this one. Okay, then category 3, terrain category 3 is characterized by closely spaced obstructions. So you can see here closely spaced obstructions. It's called suburban residential area or manufacturing districts or wooded fields. And this is the terrain category 4. So if you go to Bombay or Delhi, it will be having high-rise buildings. Then you can consider as that one as a terrain category 4. That is the local, regional, large cities or urban area. So usually, what you consider terrain category 2 for our tower if you are in the small city, something like this. Okay. So this K2 value depends upon the terrain category and height. So this, you can see in the table 2, the factor to obtain the design wind speed variation of with the height in the different terrains. So previously they used to give in each terrain category A, B, C. That they removed now and they make it only one. They made it as a one only. So selection of terrain category is very important. So according to category, where our located, you have to define the terrain, and based on that one, the values of K2 will be varying. K2 factors will be obtained for the design of speed at different heights. See here. So if we take the terrain category 1, so for 10-meter height, up to 10-meter height, it will be constant. Up 0 to 10-meter height, you have to take 1.05. N variation will be there for 15-meter, 20-meter. So it will be varying up to 500 meter that you are 1.35, 1.35, and here it will be different variation will be there. And if you want to calculate in between 10 to 15 and 12 meter, so you have to interpolate between these two. The K2 value will be variation between 1.05 and 1.09. So you have to interpolate for 12 meter. Similarly, you have to do for different terrain categories. So that is K2. Then K3 is the topographical factor. The local feature like slope and hills, valleys, or ridges, etc., will affect the flow of wind and hence modify the wind speed. So if you are constructing a tower on top of a hill, that is you have to consider the K3 factor. How tall this one from the ground level, and what is the slope, and how far it is that one. All the things it will be, there is a distance L, distance W, H, and crest, what is the here, and IS board gives you clearly how to take into consideration that for calculating K3. So it will be up to 3 degrees. So you can take K3 is equal to 1. It will vary from 1 to 1.36 for different slopes greater than 3 degrees. So it will be giving so okay. So then K4 factor, as I told you before, this will be introduced in recent code to ensure better safety of the structure in cyclonic storms. Cyclonic storm region that is up to 60-meter wide on the east coast as well as on the Gujarat coast. So they are taking from the coast point to up to 60-kilometer wide. So that value K4 they have to consider in these two regions. That is the coastal area of east coast as well as Gujarat coast. Structures the post-cyclonic importance for emergency services such as cyclone shelter, hospitals, schools, communication towers, etc. They are telling clearly for communication tower also, you have to consider this a K2 factor, K4 factor as 1.3. And another factor it will be after having K1, K2, K3, K4 will be recently they introduced the factors KD, KA, KC in IS code. So this will be wind directionality factor, area averaging factor, combination factors. This area averaging factor and combination factors it will be more effective in building other structures. For towers and skeletal structures, it will be taking as a one only. Only the wind directionality you can reduce by 0.9. So KA and Kc is equal to 111 only. So Kd is equal to 0.9. So once if we calculate what is the design wind speed, that is a Vz, multiplication of basic wind speed into K1, K2, K3, K4, and Kd, Ka, Kc. All the things will be there, and you will be getting the design wind speed. Then we need to calculate the what's the wind pressure, that is Newton per millimeter square at a different height. So this wind pressure again it will be varying from bottom to different height. So Pz is equal to, that is a Vz you are calculating wind velocity at a different height. So that's equal to Pz is equal to 0.6 into Vz square. Then design wind pressure will be Kd, Ka, Kc into Pz. That is the design wind pressure. Once if you know the design wind pressure, pressure into area will get the force. That is our intention. Why you want to calculate the pressure from how you are come from the basic wind speed, we calculate the design wind speed, then we calculate the pressure. But once if you know the pressure into area, we get the force. So that is not enough. Only so another factor, it depends upon the force coefficient. So force, whatever force will be area into pressure will be there, and also CF, that is a force coefficient. You need to calculate the force coefficient for this skeletal structure, tower structures. So that will be depends upon the solidity ratio of the tower. You see that one AE is the effective projected area. So that means whatever the members will be there, that area only have to take. So flats will be there, one side leg member will be there, other side also leg member will be there, and bracing members, all the thing length into width, what is the width of that one. For example, if we have a flat of 50 by 5, you have to take 50 as this one and length. And leg member will be 100 by 8 will be there, 100 into that length. So all the things you have to consider the projected area. AE and PD is equal to pressure on the surface. And also that a major portion of the wind load on the tower is due to the wind force acting on the tower frames, antenna and ancillary components. Ancillary components means maybe ladder or cable racks, all the things have to be called as ancillary components. So once if you know your tower configuration, how you are put whether leg member, bracing member, secondary member, and these ancillaries, all the things will be there. Then we need to calculate the force coefficient. The force coefficient depends upon the solidity ratio. Solidity ratio, how to calculate means, if we have a tower, you take just a straight. So this is the tower leg member running parallel without inclination. So most of the towers will be inclined like this. For your clarification, I will take only parallel one. So it will be there. So what are the hatchery portion you take here? So solidity ratio is equal to area of the exposed members. That means the hatchery portion divided by area of this rectangle. So that is called here solidity ratio is equal to area of AS. AS is equal to only hatchery portion divided by H into B. What is the H is equal to I into B. So this is small verification, and if you have a ancillary, so whatever cables will be there or ladders will be there, all the things will be considered ladder ancillaries. AAA. This is for the structure. AAS. Structure member area, that is a hatched portion here, and this is the ancillaries, that is AAA. If we have AAA, you have to consider that one. Divided by H into B, area of this total enclosed portion. Similarly, if it is the inclined member, you have to take the trapezoidal area here. Hatched portion, that is a AAS will be there. Area of trapezoidal will be B1 plus B2 by 2 into H. So that is H will be there. So similarly, if you have ancillary, here also they are giving AAS plus AAA divided by B1 plus B2 by 2 into H. Okay, area of the trapezoid. So that once if you know the solidity ratio, then IS code gives for different solidity ratio what is the force coefficient, whether it's a square tower or equilateral tower. So if we see that ratio, if we get 0.2, you can take directly for the square tower 3.3. So it is not just force into area. So another factor is coming here 3.3, that is force coefficient for the 0.2 select ratio. If it is a triangular tower, it will reduce. This is only for the flat members. So if we have a circular member, it will be different. If we have a flat member, it will be different. It gives a different table. So square tower with the flat member, so the maximum wind load occurs in the diagonal direction. So for here, normal wind will be there. Normal to the tower, that will be acting this P means. So 1.2 times of the P you have to take in the diagonal direction for the square tower. Okay, for the triangular tower, it is not like that. Whatever load is there, we have to apply in the normal to tower and 90° and 180°. So whereas in the square tower will be normal 0°, that is normal to surface, and diagonal 45° you have to consider. So this is the flat force coefficient for the flat surface, square tower and triangle tower. So let's just explain here. If you have a normal window here, so you have to distribute the load 0.5 P, 0.5 P. Either you can take front node or you can 0.2 by all the 4 nodes also can take, because it's acting at different level. It's only shear at that level. Okay. So all the 4 also you can consider, or 2 also you can consider. It doesn't matter. So height into the car, it will matter. So if you have a diagonal wind load, so that will be having a 45°, that is the diagonal wind will be. So if it is a P here, normal wind load, 1.2 times of P. So if you take a sin 45 cos 45, the component will be 0.424 P it will come. So you can either you can use all these 3 or 4 also you can use, doesn't matter. Okay. So if we have overall force coefficient for square tower composed of circular members, see here. So same 0.2, previously you have seen 0.2 solidity ratio, there you have seen 3.3. If it is a circular member, it will be reduced to so much, 1.9, or onto corner. Corner already they have considered as 1.2, 3.3 to 1.2 will come here, whereas here 2.2. So that is another class for the circular member that is called subcritical and supercritical. So that means that is what's the Reynolds number? DVD. DVD is less than 6 meters per second. Then you have to consider this step. If it's DVD is greater than or equal to 6 meters per second, that is called supercritical flow. You have to consider this one. If you are in the supercritical flow, still the values are reducing. Subcritical it will be 1.9, whereas supercritical is equal to 1.3. Whereas in the flat section it is a 3.3, and per diagonal this onto corner means on the diagonal into 1.2. Here it will be very less. So that means that's why the circular members will be having very less coefficient, force coefficient compared to the flat section. So most of the towers they will prefer the circular one. But one thing here, the problem, fabrication. Fabrication have to take care of. If you are not fabricated properly, it will start corroding. Okay, that is more. That's why they'll go. Most of the towers will go with angle sections. Okay, once that is how to calculate the wind load and how to apply for the different levels and different members, whether it is a tubular or flat sections. So once if you know this also how to calculate the wind load on this antenna, different antennas will be there. How to calculate that one? So maybe dish antenna, Yankee antenna, grid antenna. So like that, so many will be there. So that wind load on antenna shall be considered using the Andrews catalog. So Andrews catalog is used for the for different types of antenna. So usually Andrews catalog load gives on antenna 200 kmph, kilometer per hour. For wind speed, they give the wind load. So we cannot use the same wind load for different levels. So if you go from bottom to top, the wind speed will be varying. Similarly, the wind pressure also going, and so that's why what designer may calculate the antenna load corresponding to the different wind speed at different levels. So calculate the wind speed at that level. So So if you convert this one to meter per second, it will come 55.56. So you have seen the pressure, force. Pressure also, it is a pressure is equal to 0.6 into Vz square. It is a square factor. So Vz square divided by this 200 kilometer per hour. That will be converted into 55.56 meter per second. So this is the wind load given in the code. So that will be converted to the load required in our antenna at different level. If you are considered at 15 meter level, that is not, your pressure is only 100 kilometer per hour, then 100 by 200 only, square of that one. So whatever force they are giving is at 200 kmph. So you can convert it into kilometer per hour. So 100 by 200, that's 1 by 4 will be there. 1/4 of that one. Okay, that's clear. So wind load on the antenna and the feedback antenna, you have to calculate as per the anvil catalog. If you search in Google, you'll get the anvil catalog. You can download and you can make use of that one. Okay. So this is the different antenna will be there. This is called GSM antenna. This is dish antenna will be there. All this dish antenna and with radom, without radom, so many types will be there, and how it will be connected. These are all the connecting members. It will be there. All the things wind load you have to consider, and you can see how many numbers will be there. If you are providing the front side or back side is same. In the back side, if you consider, you can consider as a shielding effect. That also possible. So once another one, the GSM antenna, how to calculate the force coefficient. So in the antenna catalog, they have not given for the wind load for GSM antenna. So we need to calculate using the exposed area of such antenna by wind pressure and force coefficient. This force coefficient for the GSM antenna is considered as a flat CF. It depends upon the aspect ratio. So it will be given in PI triple to H. Now recently revised to H. So they given the flat numbers at this value varies from 1.2 to 2. That is CF value for GF antenna, it will be varying from 1.2 to 2. Depends upon the aspect ratio. Aspect ratio means what is the length divided by width ratio. If it is less than 2.5, you can consider as a 1.2. If it is equal to 7, 1.2, and if it is less than also, you can take as that one. If it is greater than 25, 2 you can there. In between, if it's coming, you have to interpret. 7 to 25, you have to interpret from 1.2 to 2. Okay, so that is CF value will be there. So pressure, wind load you can calculate, wind pressure will be there, exposed area of a GSM antenna, force coefficient depends upon the aspect ratio. Okay, usually once if you have the tower with different base width, the top width and middle width and all the things, approximately you can calculate the natural frequency of the tower. For freestanding lattice tower with a rectangular or square cross section, the following formula can be used. That is natural frequency, that is first port natural frequency will be 1500 into WA divided by H square. WA is the average width in meters. H is the height of the structure, height of the tower or in meters. If the natural frequency is less than 1 Hz, then the tower is, it will be dynamically sensitive. Accordingly, if it is dynamically sensitive, IS code gives different formula. Again, this whatever calculated, it will be having different methods. So that also not satisfied that dynamic effect of the wind load is to be considered. So there is one thing is natural frequency is less than 1 Hz, on the ratio of the height to that of the tower is more than 5. Then you have to consider the tower as dynamically sensitive and dynamic effect you have to calculate. The gust factor method is called. So in the section 10 of IS 875/2015 gives the details to how to calculate this wind force on the tower by the gust factor method. Now it was very simplified in the recent code. Previously they used to have so many charts and graphs and all. Now it's very simple. They have given the formula one can have in our Excel sheet and you can calculate the value of G value. So that will be it. So natural frequency, if the natural frequency 100, then the dynamic effect of the consider. In such case, the class 10 will be there. So that is force on the wind load. Wind force will be CFZ, AZ, P bars D. That is here bar will be calculating. The another factor is called G. G is the gust factor as per the class 10.2. So force you can calculate on the tower. A is the effective frontal area. PD bar will be design hourly. Previously we have taken 3-second gust. Here hourly mean wind speed. Maybe how to calculate V bar Z. So it gives in the code how to calculate V bar also they given the formula and table also given. Using that table you can directly calculate the PD bar. Once if you know the PD bar, that is you can calculate the force on the tower members on the different panels. So force coefficient will be there. Then okay. So once if you calculate all these loads on wind load, you have to distribute for the different panels. So there are so many panels. So each tower will be having maybe 10 or 15 panels. So from the top you have to distribute the load. So for example, top panel load will be there some total load of that panel, say P. On the 4 nodes of that one you have to distribute. Top 2 node, bottom 2 node. So P by 4 will be there for the first panel. If you come to next panel, so that is a P1 will be there. Next one total load will be P2. P2 by 4 again will be there. For the middle point, you have to consider P1 by 4, P2 by 4. Like that, you have to add up from top to bottom. Calculation. Now, seismic load you have to calculate as per IS 1893. The force attracted the structure seismic disturbance is a function of ground acceleration and the properties of the structure. The following are some of the important factors on which the seismic loads is dependent. It is stiffness of the structure, damping characteristic of the structure, probability of a particular earthquake occurring at a particular site where the structure is located, importance of the structure based on the consequence of failure, and foundation characteristics. So yes, 1893 they will be divided into 4 zones like this. So again, the northeast will be zone 5, and here you can see zone 4 will be there. This is zone 4. Again, the South India it will be safe. That is zone 2 will be there. Now they merged zone 1 and zone 2 into zone 2 only. There is no zone 1 now. This all yellow color it will be zone 3. Okay, or Tamil Nadu will be having zone Tamil Nadu and Karnataka. Some border of Andhra Pradesh will be zone 2. Okay. So accordingly, you have to take into consideration that how to calculate the seismic loads and all. So seismic loads mainly it will be having factor mass into maximum acceleration. So force will be there, maximum acceleration by G into mass into G. So maximum acceleration by G into weight. So that's called seismic weight of the structure. G is the acceleration due to gravity. Typically, code expresses the seismic force as VP is equal to, that is a base shear equal to AH into W. So AH will be the shear coefficient, VP is the base shear, design base shear. So once you calculate the design base shear, you can distribute the load for different levels. So it will be depends upon the what's the severity of the ground motion, soil condition, structural characteristic, that is a time period and damping, all the things it will be there. So seismic forces you have to evaluate as per 1883 part 1 and also part 4 you have to use for the stack-like structures. Okay, the AEH will be, that is the base shear can be calculated using the zone factor, importance factor, or response reduction factor. SABG, that is spectral acceleration coefficient. So AEH can be calculated using this formula. So it depends upon all these factors. So zone factor will be depends upon the ground motion. So as I told you, India divided into 4 seismic zones. In the recent code, that is 2016, they revised. Again, it's going to revise in 2022. So it may be slightly methodology will be same, but the coefficients may vary or the zones may change. And importance factor, it ensures the higher design seismic force for more importance structures, important structures. Value of structures is given in the table 8 of IS 1893. Okay. So similarly, the response reduction factor, that quick resistance structures are designed for much smaller seismic forces than the actual seismic forces that may act on them. This depends upon the ductility, redundancy, and overall strength. So the response reduction factor is a structure with a good ductility, redundancy, and power strength is designed for smaller seismic force and has higher value of R. For example, building with semi-moment resisting frames has a good ductility and R is equal to 5, as against R is equal to 1.5 for an unreinforced masonry structure. So table 9 gives the R value for buildings. For tanks and industrial structures, they given stock-like structures, no? R value given in the part 4. So you have to use IS 1893 part 4. So once if you know the base shear, we have to distribute different height of that one. Seismic weight of the tower is the sum of the seismic weight of all the angle sections. Seismic weight at any level would be equal to the dead weight of the tower system, antenna and their connections, platforms, ladder, cable racks, and also cables are to consider. The design basis here, VB, the swap time, is then distributed along the height of the tower using the parabolic distribution using this formula. So QA, QI at a different level, and this is a seismic weight, total seismic weight, and h square, different h square. So it will be distributed according to the different height. So you have to analyze it. So as I told, this IS 1893 part 4 2015 is a criteria for quick resistance structures. Structures with industrial structure, including stack-like structures. So they mentioned here transmission and communication towers and other cooling tower, chimney, silos, all the things will be there. So one you have to consider, if it is a very important structure, you have to consider seismic loads also. So once if you calculate all this load, then you have to do the analysis. I think you already might have knowing how to do the analysis of towers structures and general structures, and you have to model. Once if you model how to transfer the load to different nodal point, so different nodal point you have to transfer the load, and the connectivity, load transformation, and you have to have the different loads, dead load, wind load, earthquake load, live load will not be there, and other things you have to consider. So in the market you will be having so many softwares. I think you can use I think you may be aware Stat Pro, ETABS, SAP 2000, and if you have still very research things, you can use Abacus or ANSYS and all this. So if you are going for a research work, they'll be using this type of software. If you are going directly for the design and all, you can use ETAB or SAP 2000 or Stat Pro or MATLAB will be useful. So once you know the load calculation, so your tower configuration, you transfer the tower configuration to the whatever different software, then apply the boundary conditions, apply the different loads. So you'll be having the different loading condition. So select different, I'll just tell that one. Selection of tower configuration, computation of loads. So you've done wind load, earthquake load, internal load, platforms also have to calculate similarly. Then analyze the tower using for different loading condition. Then load combination also is very important. So as per the limit state of strength and limit state of serviceability, both you have to do. Then check the limiting reflection and standardized ratio of the members. Design the members as per the codal provisions. So these are the different tower configuration. So you may be having a configuration, maybe all the X bracing will be there, or K and X bracing combination, or K bracing will be there fully, K bracing with the secondary bracing, X bracing with secondary bracing. So one can have different configuration. You can optimize which configuration gives the minimum weight and also minimum for foundation forces. That is very important. So the design of communication towers. So here mainly all the members are truss members. It should be designed as either compression or tension. So you may already know how to design the compression member as per IS 800 2007. So here what you have to do for all the tower members, it will be reversible of loads will be there. It will be alternate to compression or tension may be there. So all the tower members, you have to design for both tension and compression. So it can be designed as per the IS 800 or 802 with load factor. For tubular sections, you have to use IS 800. Okay. So I think you already might have studied in our UG thing. It will be same procedure. There is no other thing. Only thing you should be very careful while taking the tension member. That is direction of bolt. So you should always have alternate bolting system. So these are the limit state of strength. If you see here, so for different load combinations in IS 800, use a table 4, that is a partial safety factors for loads. So as well limit state of strength as well as limit state of serviceability. So limit state of serviceability, for if you want to check the deflection, you have to use this load combination. So if you are designing a tower member, so you have to use this load combination. So I told before, the dead load and live load combination will not go out. So you have to use dead load plus the wind load. Sorry, one.
Sorry for the interruption. Take a 2 minutes break, sir.
You want to take a break?
Sir, your wish, sir. Your wish, sir.
No, no problem.
Okay,
If
sir.
you wish to take, you will take 2 minutes, no problem.
Okay. So you will continue, means you will continue, sir. Otherwise, no problem, sir.
Yeah, yeah. 1 minute. Just take some water.
Okay, sure, sir. Sure, sir.
Okay, we'll continue. No problem. Okay. So limit state of strength. So mainly you have to consider dead load plus wind load or quick load. It means we'll be having a dead load of 1.5, wind load will be 1.5. I think this will be governing condition. So another one, 0.9 times of dead load and 1.5 times of wind load, it will be governing for the tension. So 1.5 and 1.5 partial safety factor, it will govern for the compression. So if you are going for the tension, you have to check for 0.9 times of dead load and 1.5 times of wind load or earthquake load. Whereas in limit state of serviceability, you need not worry. It will be 1 1 only. Okay, live load it will not go. You check for these two conditions. It will be enough. Okay, then I'll just show you here. So load cases and load combinations considered for the analysis of the tower as follows: dead load, DL, normal wind load will be there. Diagonal wind load for a square tower, it is very important for a square tower. Load combination with a partial safety factor. So as per IS 800, will be on that one. So limit state of serviceability, it will be like this one: dead load plus normal wind load, dead load or diagonal wind load. Here limit state of strength, it will be 1 point times of dead load, 1.5 times of normal wind load or diagonal wind load. Similarly, 0.9 times of dead load, 1.5 times of normal wind load, 0.9 times of dead load, 1.5 times of diagonal wind load. So in this combination, you can, whichever is governing, that force you have to take and design for both compression and tension. governing forces for the above load combination. Consider for the axial loaded member. So compression is there, both the tension is there. So as per IS 800, if we take as per class that whatever factor design tension T will be the member shall satisfy. T is less than TD. TD is equal to design strength of the members. So you have to design the member as per the design strength due to yielding of cross section, design strength due to rupture of critical section, design strength due to plug shear. All the things you have to see, and which one is giving the critical, you have to consider for the TD value. Then Euler buckling, I think you know all the things. Euler buckling of columns. That global buckling of members happens when the member in compression becomes unstable due to its tenderness ratio and the load. So Euler critical buckling load will be, or hinge column will be P critical is equal to pi square EI divided by L square. So general formula, if you take as a critical stress, F critical is equal to pi square E. So we are interested to have KL by R. That is, K is a effective length factor, L is the total length, and R is the standard radius of gyration. That is the least radius of gyration. So KL by R whole square will be there. Pi square E divided by, this is the factor will be governing. So slenderness ratio KL by R will be there. So if it's short column means it will not buckle, it will only fail due to yielding. For long column, that large KL by R usually elastic buckling will be there. So design of compression members shall be designed as per the IS 800 class 7. So factor, that is the factored design compression P in the member shall satisfy P is less than PD, where PD is the design strength of the members, depends upon the following. There is effective sectional area, Euler buckling stress, effective slenderness ratio, non-dimensional effective slenderness ratio will be there, imperfection factor, and also partial safety factor of the material. All these factors, I think it gives clearly in IS 800. So you have to consider accordingly, you have to design that. So some client, they ask you to design as per 802. You can design the tower, but you should consider minimum load factor of 1.5. So whatever the force coming, you are going to design, increase the loads by 1.5 times. If you are going to design using 802, okay, that gives the formula in 802. This is the formula for axial loaded compression members. So it gives clearly that KL by R less than CC. CC depends upon the Young's modulus and yield stress. So CC is equal to pi into square root of 2 into 2E divided by Fy. So that value KL by R less than or equal to CC, then the value of allowable stress will be given 1 minus half into KL by R by CC whole square. Or otherwise, if it's KL by R is greater than CC, then pi square E divided by KL by R whole square. So that very clearly that it gives in 802. So all the our members, I think they're following this one. Only thing was the load factor should be used. So also it gives, so yes, 800 gives in differently, whereas IS 802, the P by T initial limit gives in different values. So that critical yield stress, it will be depending upon the P by T ratio. So if it's a P by T ratio, the width thickness ratio exceeds the limit. This is called limit given above in the formula for FPA. The variable Fy will be substituted by F critical. So whatever you in the previous way Fy will be there here. So Fy you have to replace by this F critical. So based upon your B by T ratio. So B by T ratio will be there if it is greater than limiting value, that is limiting value B by T value 210 divided by square root of F5, and also less than 378 by square root of F5. Then the value of F critical will be this is the value. If it is greater than B by T is greater than 378 divided by square root of F5, then the F critical will be this value. That means the value of Fy you have to replace by this one. It will reduce everything. So buckling patterns you might have seen here. So if you have a support without support here, it buckle like this. If you have there is a major axis buckling and minor axis buckling, it will be like this. And the local buckling will be there. Some members will local buckling because of the thickness is very small. Then it will be having the local buckling. So we have to take both the minor axis and major axis buckling for the consideration of compression member design. So if you have a support at the center, for example, it will be buckling like this. Whereas in other direction there is no support, so you have to consider the full length in that case. So here in the one direction RVV, if you are going to take as RVV is a minimum radius of gyration, so you will be taking this. This is the length. Whereas other direction there is no support. In that case, you have to take RXX divided by total length. So KLB 10 feet will be there. 5 feet, 5 feet. That is for the minor axis buckling. Whereas the major axis buckling will be K will be equal to 10 feet there. Okay, now yes, the 802 it depends upon your number of ports, how your ports are connected. And also it depends upon the value of L by R up to and including 120, then it will be KL by R equal to L by R will be there. So that is a link or joint members bolted at connections in both phases with the value of L by R up to and including 120. So L by R value, if it is less than 120, you can use directly L by R, L divided by R. L by R value they will be giving for different end conditions, whether it is one is restraint, another one is not restraint. According to that one, they gives the value of KL by RU, R value here you can see. And also for restraint members, they restrict the L by R less than 250. And leg member, here you can see leg member in the recent code, they increase the L by KL by ratio, that is the maximum value 150. For other members, is also 150, and the redundant members carrying only nominal stresses, it will be 250. And also, it's 802, it gives clearly how to take this length. For example, you will be having the secondary bracing like this. So initially I told you have to take the length. If you have 3 divisions, L by whatever the maximum length. So length it will be here, it will be less, here it will be less, and among all the 3, you take the maximum value. That is the L star is the maximum value. Then the concentric load. So this is the one phase of this one. One phase of the leg is this one. This is another phase. So here symmetrical is there. Usually all these towers will be symmetrical both phases. So in that case, that is called concentric loading. So we have to take what is the L by R value, L divided by RVB. So if it is no restraint at the end also, it will be taking L by RVB. So this is the measured length. So measured length, you have to take maximum length. So we should not take total length divided by 3. So take actual length. Actually, if you take in AutoCAD, you will get the actual length. That divided by that R minimum. That RV will be the minimum radius of gyration. So in the bracing, so if we have the bracing like the X bracing, so what you'll do here in the center to here, AB will be there. And what they are telling is this is saying, so AB divided by RVB you have to take for KL by R ratio, or AC divided by RVB or CB. Here C will be here, AC divided by CB divided by RVB will be there. So here also AC, CB and AD. So AC, CB, and AD will be considered as full RVV only. So you can see here AC, that length this one, and CB this length this one, and AD this length this one. So they will be considering that value divided by minimum radius of gyration. Whereas if you take another direction, there is no support. So AB divided by RXX RYY, and also AD divided by RXX RYY. So which was giving lesser value of take. So for example, in one phase, from one phase to another phase, they will be providing another redundant member connecting from front phase to other side phase. So from here to here, they will be connecting like this. If you see view of one, they will be connecting this one. So in that case, what will happen? AC, CB, AD. That will be there as usual. Previously, you have seen AC divided by RVV, CB divided by RVV, AD divided by RVV. And previously, you have done in the previous case, AB divided by RXX you have done. Here it is not required because there is a support at this point also. So no need to take AB divided by RXX. So in the tower, it's very important in the tower structure. So this pattern is not given in 800. So you have to refer 802 only. Similarly, here also you can see AD, DC, CB, or AE, or EF. Divided by RVV will be governing. So if you provide support like this in the hip bracing, it's called hip bracing. In the view 2-2, if you see in the middle, that is called hip bracing. From here to here, from here to here, they are connecting like this. So all the support will be DD, CC. Then it will be RXX is not required. For example, here if you are not using any support, then you have to use AF divided by RXX. That also have to check for the value for the minimum KL by R value. Okay, similarly you can do for K bracing. K bracing also AC divided by RVV, CB divided by RVV, AB divided by RXX. So similarly, if you have a hip bracing, that will be very simple. So design of communication towers, I think one another connection, leg to leg connection, and you have to calculate how many number of ports required, and how you are going to connect the bracing member to the leg member, whether the width of the leg member is sufficient or not. If it is not sufficient, that width of the leg, then you need to provide guzzle plate. Guzzle plate is providing that will be connected to the main leg member, and this all the tower members will be connected either diagonal bracing or horizontal bracing, and from bottom also diagonal bracing. So all will be connected. If you have enough space in the leg member, there is enough width, then you can provide like this only. So leg to leg connection, as I told you, they will be having the cover plate and the inside plate double. That is double shear effect will be there. So they will be connecting like this. So then another one, foundation design is very important. So base plate design, they are given the how to design in class 800. So class 7.4.3.1. So base plate design thickness, they are given the formula like this. You can make use of this formula. That is minimum thickness of the rectangular slab is equal to. So A and B, if we have an angle from the square base plate, angle will be providing. That is a smaller projection and a larger projection. So A and B that values. Larger projection will be A and smaller projection for the angle. So that will be there. A and B will be there. That value will be substituted here, and this is the uniform pressure from below the slab. Slab is under the factor load. There is axial compression from the tower. That has to consider. Then gamma M0 is the material partial safety factor. Fy is equal to yield stress. This value we will be getting the minimum thickness of the rectangle slab. So another one, anchor bolts. Anchor bolt also you need to calculate. I think this ASC, American Society of Civil Engineer Manual 52, that also for the tower, it gives the formula like this. There is a tension divided by F5 plus the shear. So we have to consider shear load also divided by U, that is coefficient of friction, into 0.85 into F5. So this is the formula for the area of anchor bolts. So accordingly, you have to distribute how many number of bolts required. And length of the anchor bolt depends upon the grade of the concrete. So how much your length is required, so that is depends upon the grade of concrete. Okay. So forces of the foundation tower will be uplift of the tower will be there, downward thrust or compression, lateral force or shear force on both directions. These are the forces that you need to consider for the design of a foundation. And the soil properties at the site investigation need to investigate from the, in the density of the soil, safe bearing capacity of soil, coefficient of friction, angle of repose. All the things are required. Accordingly, you have to design whether it is a tension or compression, both you have to check. So this tower should be subjected to both the tension and compression. So tower type, foundation type may be isolated footing, may be there, foundation, pile foundation, or rock anchor. So this depends upon your soil condition. So if you have a very good soil, then isolated footing may be sufficient. If you have very soft soil, then throughout that one, then you can either go rock foundation or pile foundation. If you have a very good rock between, you can have the rock anchor. That's also possible. So you need to check for all the things, that is downward thrust, uplift, overturning, sliding, bearing capacity, and shear checks. All the things you have to do. So another one is thing for the rooftop communication tower. So a very important thing for a rooftop communication tower, you need to check the existing tower, existing structure, whether building, how safe that one. I think we need to do non-destructive test, either rebound hammer test or ultrasonic pulse velocity, and you either you can use the performeter or you don't have know the what's the number of bars and all, or you can have the partial destructive method, whether core coating of the column, all the things you can do. So these steps need to do before taking up the work in an existing building. So loads from the tower need to be transferred directly to the existing column. So you should not put any cost on the slab. So if you because all these towers will be having the tension as well as compression. Once the wind blows, this slab will just pulls up. So we should be very careful. So before that one, you should be make sure that one all the load should be transferred to the column only by proper welding of the reinforcement required for the pedestal of the column bars, anchoring of the pedestal bars to the column by proper drilling and grouting. So this is the rooftop tower. I think I have not given any calculations and all. If somebody interested, I can show in the another next class and all. So otherwise, I'll close by this one. So if you have any questions, I will answer to you.
Yes, sir. First of all, thank you for this wonderful presentation and take a long time to sharing for your knowledge, sir. Thank you so much, sir.
Okay, thank you.
Participants, please ask your questions.
No, it's a very tough topic.
Yes,
We
sir.
should understand what's the how to design the tower members. Main thing is the load calculations only.
Yes, yes.
So mainly, if you know how to load calculate, and so many software use, because we may not be knowing how to calculate that one. You'll be using as a black box. Whether it's correct or not, we may not be knowing. So before that one, once if you know how to calculate this wind load and earthquake load and how it is taking in the software. Once if you understand the basics, then if you apply for the in the structure, you will get a good idea.
Yes, yes, sir. Participants, any questions?
So if you have taken course in the post graduation M.Tech, then they will be having the transmission and communication tower one subject. Okay. Or somebody interested to go for that tower section, they can work in a one company in tower wherever tower is there. There are so many companies are available in Coimbatore as well as in Chennai. So you have to work with them, and you can get some sort of experience, so that from starting from the site recognition survey, and you can how to calculate the wind load, how to design the tower, how to do the drawing, and how to manufacture the unit, how to manufacture, how to transfer the all the elements and the tower in that site. So there are so many softwares. Which of the most used software for design of towers? There is a software called PLCAD. I think BOCAD will be there. PLCAD, especially for the towers. They will be using that one. And usually, I think StatPro and ETAPS, I think it gives a fairly good result. I think you can make use of that one. And BOCAD and PLCAD, it gives a full starting from the wind load calculation to up to design drawing and everything it will come. Any other question? Okay, software. I think you can use EDAP and software for learning how to do this modeling.
Yes, sir.
So that is commercially available software. If you join any company, you will be exposed to such type of software. I think I have taken a long time.
Yes, yes.
Okay.
Yes. So now I complete this section, sir.
Completely.
I completed this section, sir.
Okay.
Yes, yes, sir.
Okay. Given opportunity for sharing my knowledge to your students and the research scholars as well as practicing engineers. If you have any question or anything, you can contact me. I will be available anytime. Okay.
Yes. Okay, sir. Thank you, sir.
Okay, thank you very much.
Thank you.
Okay, bye.
Bye. Participants, please fill your feedbacks form for your future certificate. Certificate will reach in within 5 days. Please fill the feedback form. Yes, sir. Is there in YouTube also? I will share your mail ID.
So you want mail ID? I can put it here. ABC.ac.in and WhatsApp number 944554542. This WhatsApp number.
Any doubt for this transmissions or any classes, we'll ask this sir. Sir will be put the WhatsApp number and email ID in this chat box also. You will use it for your future reference. Okay, sir. Thank you.
Okay,
Thanks.
thank you very much. Bye.
Thanks. Participants, please fill the feedback form.